Okay, so here's an improper integral. I think this is similar to one of the multiple choice problems on the Calc 2 exam from last fall, but I don't know exactly which one, and I think it might be a little bit more challenging. So we're doing an integral. It's clearly an improper integral because we have an infinity here. But there's another reason that could be improper, because we've got a rational function, and whenever the denominator is equal to 0, we're going to have an asymptote, or potentially have an asymptote depending on what the numerator is. But we definitely have an asymptote for this when the denominator is 0, that is when x is equal to 0 or x is equal to minus 1. But notice we are not integrating on those values. So our interval goes from 2 to infinity, but this integrand is continuous from 2 to infinity. There's a discontinuity at 0 and a discontinuity at minus 1, but there's not a discontinuity on this domain of integration. So this is just a infinite, I can't remember if we call this type 1 or type 2, infinite domain. This is an infinite domain improper integral. The domain referring to the interval of integration. Okay, so this integral is defined in terms of a limit, and we'll get to that limit in just a moment. But notice I'm still going to have to find the antiderivative of 1 over x times x plus 1 squared, which means I'm going to have to do partial fractions. So this is an improper integral problem combined with a partial fractions problem. So we're going to have 1 over x times x plus 1 squared. Okay, x plus 1, this is a linear factor, so the form is going to be a over x plus b over x plus 1 plus c over x plus 1 squared. And now my next step is I'm going to clear denominators, and I'm going to get 1 is equal to a times x plus 1 squared plus bx times x plus 1 plus cx. Okay, I'm going to have to erase all of this work, but I'll keep it up here, of course, while I'm doing it. Okay, so the first thing that I want to do is I'm going to set x is equal to 0. If I set x equals 0, the equation becomes 1 on the left-hand side equals, well, a times 0 plus 1 is just going to be 1. B times 0 is 0. C times 0 is 0. So this tells me a is equal to 1. OK, I'm next going to plug in x equals minus 1. When I plug in x equals minus 1, what does the equation become? Well, the left-hand side stays 1. On the right-hand side, I'm going to have a times minus 1 plus 1. That's 0. I'll get 0 here. C times minus 1. So it says 1 is equal to c times minus 1. In other words, c is equal to minus 1. Now for b, there's no clever value I can plug in that's going to make the other terms go to 0. So I'm just going to look at the coefficient of x squared on the left-hand side. The coefficient of x squared on the left-hand side is 0 because, there's like a 0 x squared plus 1 here. So I've got 0 over here. On the right-hand side, I can get an x squared term here. When I sort of factor this out, I'm going to get x squared plus 2x plus 1. So ax squared, a is going to be the coefficient of x squared from this term, and a is equal to 1. Over here, the coefficient on x squared is going to be b, because x times x gives me x squared. And then over here, there is no coefficient on x squared. It's just x. So this tells me that b is equal to minus 1. OK, and so this is the partial fraction decomposition that I'm going to use to compute the integral. Notice I can do the partial fraction thing without even talking about the integral. This is just something that's true for, for all values of x for which this function is defined. We will now use this to compute this integral. OK, so by definition, this improper integral, the integral from 2 to infinity of dx over x times x plus 1 squared. This is equal to the limit as r goes to infinity from the integral 2 to r, and now I'm going to replace my integrand with its equivalent partial fractions decomposition. So this is going to be 1 over x minus 1 over x plus 1 minus 1 over x plus 1 squared dx. Okay, and so now this is equal to the limit as r goes to infinity. Okay, let's see if we can do all of these antiderivatives in our heads without actually having to write down and do anything, doing any explicit u sub. So the antiderivative of 1 over x, this is the natural log of the absolute value of x, but x is only positive here, going from 2 to r, so this is just the natural log of x. Okay, so let's think about the antiderivative of 1 over x plus 1. Let's do a little scratch work over here. So I could think about saying, u is equal to x plus 1, then du is equal to dx, and then the integral would become du over u, which is the natural log of the absolute value of u plus c, and this is going to be the natural log of the absolute value of x plus 1 plus c, but we don't care about the plus c when doing a definite integral. Okay, so you can't see it. I went off the board over here, so this would x plus 1. Okay, so this is now minus the natural log. Again, it's going to be the absolute value of x plus 1, but x is positive. X goes from 2 to r. Those are positive numbers. Therefore, x plus 1 is positive. So this is the natural log of x plus 1 minus, and I can do something similar. Again, let me do a little scratch work for this. I could say u is equal to x plus 1. Then du is going to be equal to dx, and the integral would become du over u squared. This is the same as u to the minus 2. So this is going to be minus 1 over u, which is equal to minus 1 over x plus 1. But again, really, it'd be good if you could do this sort of thing in your head. So this is now going to be minus. So I've got a minus sign here, but the antiderivative of this is minus 1 over x minus 1. So altogether, this is plus 1 over x plus 1. And we're evaluating this from 2 to r. Okay, so I'm going to combine to sort of condense things. I'm going to combine this log into one term. So log x minus log x plus 1 is equal to log x over x plus 1. And then plus this term, 1 over x plus 1, and we're evaluating this from 2 to r. Okay, so don't just take the limit here. You actually have to plug in the r and the 2. So this is going to be equal to the limit as r goes to infinity. When I plug in when I plug in r, I'm going to get natural log of r over r plus 1 plus 1 over r plus 1, and then minus, okay, I'm going to have to erase this now. Okay, and then minus, I'm going to plug in x is equal to 2, and I'm going to get natural log of 2 over 2 plus 1. Of course, that's 3, plus 1 over 2 plus 1. Of course, that's 1/3. Okay, and so now what's happening here? Well, natural log is continuous, so I can interchange the limit and the natural log. So this is going to be the natural log of the limit as r goes to infinity of r over r plus 1 plus, okay, well, let's think what happens here. If I look at 1 over r plus 1, so there's parentheses like this, 1 over r plus 1, as r goes to infinity, 1 over r plus 1 goes to 0, so that's going to be equal to 0. And then minus is going to be the natural log of 2 over 3, so that's minus the natural log of 2/3, and then 1/3 minus 1/3. Okay, now what happens to this limit? This limit is going to be equal to 1. As r goes to infinity, r over r plus 1 goes to 1. So this is going to be the natural log of 1, which is 0. So this is equal to minus the natural log of 2/3 minus 1/3. Now you might be a little concerned because we have minus signs here, but we're integrating a positive function. This 1 over x times x plus 1 squared, this is positive on the domain of integration, but it looks like we have something negative here. But remember, I can move the minus sign to the exponent of the integral, and this becomes the natural log of 3/2 minus 1/3. Okay, and this is going to be greater than 0, whatever it's equal to. Okay, and so that's it for this problem. Again, two things, or several things to keep in mind here. It could be improper because we have the denominator. This is discontinuous when x is equal to 0 and minus 1. We're only integrating from 2 to infinity, so therefore it's only improper because of an infinite domain. Improper integrals like this are defined in this way. This is the definition of an improper integral, and we did partial fractions to be able to compute the antiderivative of this. Also, the side calculations over here, when we computed the antiderivative, if you didn't follow what I did over here, pause the video and figure out what's going on. But at this point, to be efficient, and because you've done so many problems at this point, it's good to be able to go straight from the function to its antiderivative without having to do a lot of work over here.